Hello, Math 1224. This is Dr. P with Lesson Supplement 3.04. This video is a response to those of you who were asking questions, and I know that I've partially answered these questions, but haven't given what I think is a complete answer to the question. When you're integrating something by parts, how do you pick the parts strategically? Because there are multiple ways you can pick parts, but sometimes you pick parts in a way that doesn't make the problem easier. I feel like if I say pick parts anymore, I'm going to stumble over my own words. It's like a tongue twister. It's like Peter Piper or something. Anyway, take a look at this integral, 3x squared times the cosine of 5x dx. Now I'm starting with one that you've probably seen something like this before and probably have some idea how to do it, but I'm using this as an example to illustrate a general principle here. So here in this integrand we see, let's get another color here, we see essentially two parts, this one and this one, and we're going to end up joining this dx with one of those two. So we need to decompose this as u times dv. And really, even though there are a number of different choices you can make, there's essentially really two choices. One choice would be, let's call this choice 1. Choice 1 would be set u equal to 3x squared, and then dv equal to cosine of 5x dx. All right, and then let's just go ahead and work out what du and v would be. Du would then be 6x dx, and v would be, well, what's the antiderivative of cosine of 5x? I think that would be 1/5 sine of 5x. I think, you might want to check yourself and make sure that that works, but I think that works. Okay, so that is one possible choice. And then the other possible choice, let's zoom out a bit, give me a little more room to write here. The other choice, and let's put it in a different color, let's put it in green. Choice 2 would be, let's pick dv to be 3x squared dx, and then u to be cosine of 5x. Okay, in that case, du would be -5 sine 5x dx. Sorry about that. And then v would be, let's see, what would v be? V would be x cubed. Well, that's kind of nice. All right. But then whatever choice we make, we have to deal with the consequences, and those consequences are determined by the integration by parts formula, which is the integral of u dv equals u times v minus the integral of v du. Sorry, that's a little bit hard to read. I'm going to rewrite that. V du. That's a little bit better anyway. Okay, anyway, in choice 1, let's just work out what each choice is going to produce here. In choice 1, we're going to wind up with the integral of 3x squared cosine 5x dx. That's going to be uv. Uv up here, uv would be 3x squared times 1/5 sine 5x, and then you'd be subtracting the integral of v du. That would be 1/5 sine 5x. I'm just going to do a little bit of consolidating here. Minus 6/5 x sine 5x dx. Okay, so that's a little bit better. It's not a ton better, but it's a little bit better because now I have just a constant times x times sine of 5x there. And one more integration by parts will take care of that. Now let's see if the green approach gives me anything easier to deal with. The green approach would give me, that's choice 2. That approach would give me integral of 3x squared cosine of 5x dx. That's going to equal, let's see, what would u times v be? That would be x cubed cosine 5x minus the integral of v du. That would be -5 x cubed sine 5x dx. Okay, now if I look at that, look at what that produces. Well, this is fine. Okay, that's done. We don't need to integrate that anymore. But now I've got this piece here, and that's got an x cubed times the sine of 5x. Now, I realize that what I'm saying has some instinct embedded in it, but if I started with something times x squared times cosine of 5x, getting to something cubed, x cubed times sine of 5x, not going to be much of an improvement, really. I mean, I could try doing integration on parts by this, but probably the choice I'm going to make is going to take me back to having x squared times cosine of 5x. So really, choice 1 seems to be the more promising one. Now, I'm not going to finish working that one out. I just did this to illustrate that one direction takes you towards something that's a little bit nicer. And again, one more integration by parts, taking this x, or 6/5 x if you like, taking that as u, and taking sine of 5x dx as your dv, that should finish the problem. It's a little bit of a mess, but it will finish. This one, I don't think we've made things any better. So anyway, I don't think that any principle when it comes to this stuff is general enough to work all of the time, but this probably works most of the time. If you see a polynomial times a trig function, where that trig function is a sine or cosine, you're probably better off differentiating the polynomial and integrating the trig function, because integrating the trig function doesn't make it worse, but integrating a polynomial will make it worse. All right, so that's one example. Let's do another one. Suppose I give you the integral of x squared natural log of x dx. Now this is one that I think you've met in class already. But again, two choices I can make. I can either differentiate this part and integrate this part, or I can, I'll just highlight here, or I can differentiate this part, the natural log of x, and then join these together and integrate that part, integrate the x squared dx. All right, so think about which of those you would choose. I'm going to just switch colors here again. Switch to blue. Okay, so choice 1 would have, let's see, what was it? It would be u equals x squared dv equals natural log of x dx. All right, and I like this choice. I like it a lot because this means I'm going to differentiate that x squared. That makes that simpler. But then my du is going to be 2x dx. All right, that's fine. And then v is, and you know what, it occurs to me, I don't really know off the top of my head what the integral of natural log of x dx is. I'm not sure if I have at hand an easy integration rule for that. There might be one in the table, I'm not sure. I think it's probably there. But I'm not looking at the table, it's not in front of me right now, so I don't know where to go from there. All right, well, let's see if we can work out what choice 2 would look like. Well, choice 2 would be, let's pick u to be natural log of x, which makes du equal to 1 over x dx. And then let's pick dv to be the rest of that. That's x squared dx, which would then make v equal to 1/3 x cubed. All right. Now this I like a little bit better just because I can figure out what du and v are. It doesn't take an encyclopedia to figure that out. So let's see if we can work choice 2 into a solution of this problem. So by the integration by parts formula, I'm going to have u dv, integral of u dv, which is x squared natural log x dx. Okay, same thing I started with. That's going to equal u times v. That's u natural log of x times 1/3 x cubed. So I'll just rewrite that as 1/3 x cubed natural log of x minus integral of v du. So v du 1/3 x cubed times 1 over x dx. And at this point you might be saying, that sounds promising. I get to multiply by a 1 over x. I'm totally game for that because I've got a 1/3 x cubed sitting right there for me to multiply that by. So that's going to be the integral of x squared natural log of x is going to be 1/3 x cubed natural log x minus, and then simplifying that I get the integral of 1/3 x squared dx. And I think you know how to integrate that one. Let's just finish that off there. I get 1/3 x cubed natural log x minus, let's see, what is that? That integral is going to be 1/9 x cubed. And remember, that's my last integral on that side, so I need to put a constant there and make sure I'm accounting for all the antiderivatives. And there we are. I believe I'm done with that one. So it turned out that in this particular case, let me just move back up here. In this particular case, taking this and differentiating it, that sort of left me stuck, because differentiating this means I have to choose to integrate this. And I didn't know how to do that. But I could differentiate this and integrate this. And while integrating does make that x squared a little bit worse, and I'm using worse in quotation marks there, differentiating this makes things all better. Brings me to the point where I can easily integrate this thing. So there is some strategy in picking which part you're going to differentiate and which part you're going to integrate. And I'll just give a summary of those. So there's, roughly speaking, 5 different types of functions we deal with all the time in calculus. And those 5 functions are what I call algebraic functions. Algebraic meaning polynomial or rational functions. Meaning they're algebraic in origin. And then there's also trigonometric functions. And exponential functions. So exponential meaning something like e to the kx or 2 to the x, something like that. And then we also have logarithmic functions. And we have inverse trig functions. Now those are not the only functions in the world, not by far. And they're not even the only types that we see in calculus, but those are the 5 most common types. Now among these, algebraic functions, polynomial, rational, well, especially polynomials, more so than rationals, really. Polynomial functions, I know how to differentiate them. I know how to integrate them. I can do either one, but differentiation on these will usually make them simpler, more manageable. All right. With trig and exponential functions, really, honestly, I don't care whether I differentiate them or integrate them in terms of level of complication. I know how to do both. And really, differentiating any of these, integrating any of these, not going to make them that much different. You know, the integral of sine of x is negative cosine of x. The derivative of sine of x is positive cosine of x. In terms of complication, there's no difference between differentiating and integrating. Okay, now take these on the other hand, logarithmic functions. I don't even know off the top of my head how to integrate one of those. I don't know, for that matter, how to integrate an inverse tangent function or inverse sine function. Not off the top of my head. Integrating makes those way worse, far worse. So in terms of order of preference, I would much rather have to integrate one of these. It won't make things worse. If I have to, I will integrate one of these. At least I know how. I would much rather not integrate these. I'd much sooner differentiate them. So if this is a scale, then I would say this is the integrate end of the scale. And on the other end would be the differentiate end of the scale. And sometimes I remember this scale. I can usually put it together mathematically if I need to, but I usually remember this scale by looking at the first letters. Dilate I, which is what always happens when I go to the optometrist. They always want to dilate my eyes. Anyway, so if you're looking for some kind of strategy to get started, again, no strategy when it comes to this stuff works 100% of the time. But on most examples, if you want to pick the parts in the most strategic way, just remember, dilate I. Anyway, that's the end of this video. Hope you enjoyed it and found it useful, and I will see you later.